always like to just kind of pause and summarize here. We're into this last unit. It's on exponents and logarithms. So we've been messing around with exponents. You did some stuff without a calculator early on. That was pretty hard. But now we are looking at other pieces of exponents. We graphed them the last few days. You guys did really well with that. You took a little mini check on it yesterday. And now we're going to kind of just turn over the next leaf, which is applications of exponents. Sometimes applications, kids would prefer not to do, but I like to think and hope that you'll agree that these problems start to help you understand this. Well, it's called the exponential model, y equals ab to the x. So sometimes when you look at the problems we do today, you actually start to understand it more. At least that's the hope. Now, sometimes we use a calculator, sometimes we don't. It's just part of math. This is actually one of those days where you want to have a calculator. Seriously, it's not just to punch in some simple numbers, but it's to, well, you'll see. It's to fully work out some of these applications. So I encourage you to have a calculator. Otherwise, you're going to be missing out on a piece of today. Now, I gave you a little note guide this time. Hopefully, that just makes it easier to follow along. So use that note guide. And yes, the homework is even on the back. It's already printed back there. But let's start at the beginning. Okay, because ab to the x, this thing called the exponential model, is a simple formula. I hope you agree with me. It only has like a few parts to it. It has a coefficient of a, it has a base of b, and then it has this exponent of x. So it's a pretty simple formula, but it's actually used for a pretty powerful application. And the simple fact is it's used for percent. I think if you fill in the blank at the top, you'll be filling in the word percent. But I want you to realize that this is the formula for percentages, for percent change. Now, we all know what percentages are, but when we start to work them into this formula, we find out that we can slightly elaborate. We can slightly elaborate on a, b to the x. And this is for that big box. There's a big box where you can jot down sort of this new version. Even though it's a new version, there's really only one piece that has been expanded. And I hope you notice as you jot down what's inside the parentheses is now slightly been expanded to be 1 plus or minus r. Look at those parentheses. Again, it's been expanded to be 1 plus or minus r. And the reason we have r somewhat highlighted is because, well, that is your percent. You're going to find out that one of the main things today is to focus on the percent, and I just want you to notice, again, it's the letter R. Now, it's always being compared with, or we should say added or subtracted with 1. I wonder why it's the number 1. Well, if you think back to the last few days, we're always looking for numbers that are either greater than 1 or less than 1. So if we add, if we subtract, that's where we get that idea of being greater than 1 or less than 1. Let me say a little bit more where I hope you have some space to kind of point at some of these letters. Probably not a big surprise that the formula will equal the final value. Most of the time, that's the way formulas work, right? The equation is equal to whatever's the final value. Now, if you're like, what do you mean the final value? Well, the final value of whatever it is we're analyzing. Maybe it's money. Maybe it's people. Maybe it's something else. It's whatever the final answer will be for what's changing. Now, as we already learned, the number in front of the base, the number in front is the starting value. Now, again, you already learned that, and I'm referring to the graphs that you did the last few days. So that's good news. It's the same thing. This is the main thing. The letter R is the percent. The letter R is the percent. Now, there's some things we want to realize, and that's the goal of today's lesson, but percents, first of all, are always, or I should say almost always, changed to decimals. So that's the case today. You also are going to want to carefully decide if it's growing or decaying, and you'll decide based on either the language of the problem or the way the numbers are presented. But you got to be careful, got to pay attention. Is it growing by a percent or is it decaying by a percent? Well, that's going to dictate the plus or minus, as we said. Okay, more on that. I mean, that's really the point of today's lesson. Interesting, when you're looking at percent change, the exponent, well, I'm sure you can imagine, is time. Yes, the exponent is time. It could be any time. It could be seconds. It could be minutes. It could be years. It's whatever the percent, it's whatever the time is for the percent. Now, something I like to do before we do like a traditional word problem is to do more of like a just analysis of a table of values. It's already printed on your paper, but it's the same one here. You see, sometimes we get into things that are so complicated that we forget kind of about the basics, which is to be able to realize that math is essentially patterns, and patterns can turn into equations. Again, that's really what ultimately that math is. So there's a pattern represented by these numbers. Let's first see if we can figure out the pattern, and then we'll see if we can come up with an equation. Now, this is just something to just kind of observe. You know, how are the numbers changing? How is 4 changing to 6, changing to 9, changing to 13 and a half? You don't have to really punch anything in your calculator, I don't think, to see how those numbers are changing. Well, first of all, I know it's pretty obvious, but are the numbers growing or decaying? Well, they're definitely growing, right? So they're going to be going, obviously, up. How are they growing would be the main question. Well, some students would say, well, they're not changing by the same amount. Well, you're right, they're not changing by the same amount. This one changed by 2, this one changed by 3, and this one changed by 4.5. But they are changing by the same percentage. This is kind of the new way of thinking, at least this year. They are changing by a percentage. What percentage? Can you agree with me? Can you kind of notice that we're gaining half of what we had before? Half of what we had before would be the number 2. So I'm gaining 2, and boom, I get to 6. How about the next gain? How about the next gain, 6 to 9? Do you notice how I'm gaining half of what I had before? I had 6, so half of that is 3. 3 more. I'm gaining 3 more. I get to 9. And then half of 9, now that's a decimal, but half of 9 is 4.5. So I gained that. What does it mean to gain half of what I had before? Okay, well, in percent terms, that is to say that we are gaining 50%. We're gaining 50%. Now you can jot that down. You can jot that down. But what I really want you to understand is that's how these numbers are changing. Now, if we're gaining 50%, then we could start to fill those ideas into this formula. And the place that we're going to fill them in is for, let me use the letter Y. I'd like to use the letter Y. The place that I can fill that in is for the base. And as you can see here, I chose a plus sign. And then I changed 50% to a decimal. And now we have ourselves a 1 plus 0.5. The formula seems a little bit incomplete and that's because it's missing the initial value. And the initial value, it's not really a trick question. It's just a number that matches up with 0. So we don't have to think too much about that. We can just say it's 4. If you simplify this equation, you see that the base can be added to become 1.5. Okay, now that's simple equation. Whether I use y equals or v equals, that simple equation represents that pattern of numbers. But I want to show you something. I want to show you something basically on your calculator, because, well, what if it's not so easy to see the percent? Okay, this problem was meant to be easy. It was meant for you to say, yeah, that's 50%. That's pretty easy to see. But what if it's not so easy? If you do a simple division of the numbers in the table, now notice the order that I'm dividing the numbers. For example, 6 divided by 4 or 9 divided by 6. If I do a simple division of the numbers in the table, notice what I get. Okay, well, I want you to notice that you get the base. Okay, now this simple division concept will always give you the base. But again, I want you to see that it gives us this version of the base. Okay, it gives us the version that already has the 1 added to it. Okay, but it's a real slick way to be able to come up with the base. Now, the way that I divided is simply, well, the second number divided by the first number, or the next number divided by the previous number. It's not real hard to do, but you have to do it in the right order. Okay, again, I just kind of want you to process that when you do that, you get the base. However, the rate is inside the base. So again, when we see a base of 1.5, that means the rate would be the 0.5, or the 50%. Sometimes students will correctly conclude that what we're going over isn't the hardest thing ever, but there's some small nuances. And again, one of them is when you divide, you have to make sure you divide the second number by the first number. You have to divide in the right order. And you also have to realize that when you divide, you get the base. The base is important, but inside the base is the rate. And the rate is always, well, it's always the difference with the number 1. You'll see, we'll do it for another problem, which is a tad bit harder. So just like the problem that's on your, oh yeah, and so of course, if I say that it's 50%, then it would of course be 50% growth. Let's look at that next table. It's already printed on your paper. It's probably a little easier to see on your paper. What are we trying to do? We're trying to come up with an equation. Now, it's pretty obvious that those numbers are going down. I know it's kind of easy, but those numbers are going down. So the first thing you want to realize is that this is going to be a decay problem. It's going to be decay. It's also pretty easy to see that 5.3 down to 3.5 down to 2.3, those numbers are not changing by the same amount, but they are changing by the same percent. And the reason we know that is by doing a little simple division. Okay, now you have to be willing to try. Now remember, you have to divide in the right order, so it's the second number divided by the first. So I do like 355 divided by 533. or 237 divided by 355, or 158 divided by 237. Now this time I chose to divide all three of them because since there's been a little bit of rounding, we can start to see more of a pattern when we finally get to the last division. Okay, now the conclusion here, or I should say the little pattern here, is to realize that the base is 0.66, okay, or 2/3. That means that my equation will be able to have a 0.66 or a 2/3 as its base value. Okay, again, if you're trying to keep this simple, if you do the division, you'll always get the base. That means that my equation will have a 2/3 to the x. Now, the starting value, whether you want to call it the letter A or whether you want to call it the letter C, it doesn't really matter, but the starting value is supposed to be the number that matches with 0. If we look carefully here, we would conclude that that is not given to us. That's not a big deal. I just need to solve for A. Now, to solve for A, you can take any point up here like we've done before, and you can plug it in. You can plug it in for X and Y. Okay, maybe I choose to plug in the first point. That means I'll plug 533 in for Y, and we'll plug, well, 1 in for X. That's kind of nice to plug in 1. That makes it easy to solve that equation. Now again, it's a simple equation, but make sure you can solve it on your calculator. You should be taking 533 divided by 2/3. Again, make sure that you're comfortable doing that on your calculator. Maybe you have to use parentheses or your fraction key. But we divide both sides by 2/3. And we end up with an A value of, now we're going to kind of round that. Since we had some rounding early on, we'll round that up to 8. When numbers change by 1%, they will fit into the exponential model. Whether I use the y equals version, or as we'll do in a moment, the v equals version, the numbers fit into the model. But don't forget what a model is. A model is able to describe a pattern. If I want to, I can check my answer. I can plug in some x values, like maybe an x value that's up there, like maybe an x value of 4. So if I do 8 times 2/3 to the 4th, I find out that I'm looking pretty good. If I do 8 times 2/3 to the 3rd power, okay, all we're doing is confirming that the equation we came up with is right. But what I really want you to understand is, as we already said, the base is 2/3. But that means, and again, this is actually the part of the lesson that honestly I really want you to understand, that means that the rate, now be careful, the rate is always the difference with the number 1. So you have to be able to look at 2/3 and either mentally or physically subtract it with the number 1. Now, when I subtract it with the number 1, it would kind of be like I'm doing 1 minus 2/3. But that's just going to come out to be 1/3. The rate is 33% decay. The rate is 33% decay. And I don't know, maybe it's a little just confession from the teacher, or maybe you would agree, but the confusion I find from students, or trying to help students, is to realize that these numbers are changing by 33%. They're decaying by 33%, which means the base is 2/3. Yes, these two numbers are different, but they're connected to each other. Okay, and I want to help you further understand that connection through some more traditional application, okay, which we're going to slide into now. This time we'll use the V equals version of the exponential model. I forgot I had that up there. Let's skip back to that equation. I want to go through these three applications with you. Okay, well, you'll continue to understand how we can kind of plug in appropriately to our model. Okay, the first situation here has to do with a population that's growing. Okay, just look at it. Pretty simple situation, school district population. Now, there's one piece of information that's left out. That's because the population of the school district does change weekly. I'm going to confess I didn't look it up this week, but when I did ask those in charge, we were pretty close to an enrollment of 5,300. Let's just use that number, that there's approximately 5,300 students in the school district. Now, because this is a percent problem, which is actually the case for everything in the next few days, it fits into the exponential model. That means I can insert my starting value for the letter C. That means I can create my base. Now, the base is always going to be 1 plus or minus r. In this case, the population is growing, so certainly choose a plus. Now, 2.5% on a good day, if you change that to a decimal, it's 0.25. Be careful about that. Okay, remember, you always move the decimal 2 places. And then, well, if we're going to project the enrollment for 2027, we can say that, well, that would have to be 6 years from now. Notice how the time matches the percent. In other words, the percent is per year, and so the time is in years. Now, this is not a real hard problem. When it comes down to it, you can add the number 1, which that's pretty easy to do. If I add the number 1, it just becomes 1.025. And now with your calculator, you can do a little exponent. You can do a little multiplying. Now, here's what I want you to understand. This formula finds 2.5% of the first year, and then it finds 2.5% of the next year, and then it finds 2.5% of each year, and is able to add that all together to be your final amount after 6 years. In other words, you don't need to find 2.5% and then another 2.5%, because the formula does it all for you. Okay, and that's kind of the power of the exponential model when you have percentages. Again, that's a pretty straightforward problem, but it sets us up for the next situation. So same thing, just take a look at that one about a computer. Now I have a question for you. If a computer is only worth 5/8 of its previous year's value, if the computer is only worth 5/8, then blank. What does that mean in terms of the value of the computer? What does that mean if it's only worth 5/8? Then blank. Well, just kind of a simple question. Is it gaining or losing value? Again, pretty simple question. If you're only worth 5/8, are you gaining or losing? You're losing. Okay, you don't have as much. How much are you losing? How much are you losing? Now, I get it if you're a little bit shy maybe to answer because sometimes kids aren't sure. This is a new idea, but if I'm only worth 5/8, that means I've lost. Which one of these numbers is the rate? Which one of these numbers is the base? And are you processing that those are two different things today, but they're related? Which one of these numbers is the rate? The rate is the 3/8. Now that means that that's like the R value. That means that's like the percent. That also means that this one has to be the base. So I want you to think about something with me. I know you just want to kind of get the answer, which we're going to do. Okay, we're going to plug in 119 for the final value. By the way, that is something to process. 119 is the final value. We don't know the initial value. We don't know what C is. But what I really want you to understand is that in the parentheses, we either can do 1 minus 3/8, okay, because, well, as you already told me, we're losing, and you already told me the rate is 3/8, so we're simply plugging into the formula like it kind of says. Or you can just go to a base of 5/8. And I hope that you're sitting there saying, well, yeah, they're both the same thing. Right. So you can either do 1 minus 3/8 if your brain kind of works that way, or you could say, wait a minute, that's just going to be 5/8 anyway, which of course is the base. It looks like it's 6 years again. I'm not sure why I like the number 6 so much, but the exponent is 6 again. Whenever you have a percent change, it fits into the exponential model. The exponential model requires you to do 1 plus or 1 minus. Now, on a calculator, you also want to be comfortable with the algebra. The algebra here would say that I need to solve for C, which means I'm going to need to calculate 5/8 to the 6th power. Okay, now if you do 5/8 to the 6th power, you get this sloppy thing. Or you can say, okay, yeah, we're just going to be dividing both sides by that sloppy thing. And so it's kind of up to you if you want to type it all in at one step, if you want to break it down. I actually want to show you that we could take 119 and just divide it by 5/8 to the 6th power. I encourage you not to copy down the decimals or not to round the decimals. Okay, you don't want to round the decimals too soon because it can really affect your final answer. Make sure you know your calculator. Again, we're just dividing both sides by that decimal, but I'm trying not to round it. And you end up with 2,000. Now, that's a pretty expensive computer. And just kind of by the way, that's a pretty severe depreciation. If you're losing 3/8 of your value, you're almost losing half of your value. Again, that's a pretty severe depreciation. Maybe I exaggerate a little bit, but electronics do depreciate, as I'm sure most of you know, with that mobile device. Okay, it costs a lot, and eventually it's worth a little. Okay, but electronics do depreciate by a rate. Now, all of this is kind of building up to this last problem. So hang in there with me as I'm trying to show you something different every time. We've got this world population problem. Okay, now It says that it grows exponentially. I have that underlined because as soon as somebody gives you kind of the green light that something changes exponentially, that means there's a percent. Okay, so it's because it's exponential, there's a percent. If you look at the problem carefully, you might say, what is the percent? Okay, and that's kind of exactly the point of this problem. What is the percent? Okay, I shouldn't have pulled that screen up because maybe our calculator can help us with that. Looking at those two pieces of data, 1950 and the year 2000, there's a percent that's inside of them. However, there's a problem. We're on the right track, but there's a problem technically with saying that we could just divide. And maybe you're saying, well, what's the problem? I thought you told me we could divide the second by the first. Well, I'm kind of curious if you can provide any input. What would be the problem with saying that the percent is, I don't know, I'm not sure how you're going to interpret this number, but go ahead. Okay, that definitely has a lot to do with it. Oh, wait, then maybe I can take this and divide it 50 times. Okay, well, again, I want to kind of share nicely that there's a problem with that, but at least we're a little more in tune with what Isabel's saying, that they're 50 years apart. Okay, again, the percent. Now, if you looked at this, you would interpret that as 5%, but I want to stand here and say there's a problem with that. It's not 5%, but we're getting warmer. Okay, what I want you to realize, now I'll slide this screen up. What I want you to realize is that you have an exponential model. The exponential model has a percent in it. What am I talking about? Well, again, I'm talking about this formula. And this is the problem that's supposed to make you guys aware that I can use that formula to find a percent. How? Well, I got to be able to plug stuff in for V, C, and T. Okay, now V is the final value. If you look at your data, we could argue that the year 2000 is our, quote, final year. So I'll plug 6.5 in for my final value. That would, of course, mean that 2.5 is my initial value. And I think I have a time that goes with those two populations. Of course, it'll be 1,000, that's why it's going to be 50. Just let this sink in a second. This is a really nifty way to find a percent. I think everybody would agree that that's the variable of interest here. Okay. The next thing I hope you agree is that we need some algebra. We need some algebra. Now, we've talked about this kind of algebra throughout the year, maybe other years, but let's just be reminded that to solve this thing for R, I kind of have to work from the outside to the inside. To work from the outside to the inside is to first divide. I think about 2 minutes ago, we did divide 6.5 and 2.5. Interesting. We did divide 6.5 and 2.5 a couple minutes ago, even though we said that that was the wrong thing to do. Well, it was the wrong thing to do a few minutes ago, but it was on the right track. And here's where I hope that you have a little bit of an epiphany, which is what to do with the 50. A couple minutes ago, we said divide by 50, but that was not right. And I hope that you would feel like dividing by 50 would be some strange algebra, because dividing by 50 is not going to cancel that. So how do you cancel that 50? This might be something you haven't seen before. It's not hard, but you might not have seen it. I can raise both sides to an exponent. I can raise both sides to the 1/50. It's called the reciprocal. So I raise this side, I raise the other side now to the 1/50. Just by the way, that cancels the exponents. But now in your calculator, you're trying to do 2.6 to the 1 over 50. Make sure you know your calculator. A lot of them will require parentheses around 1 over 50. Use your exponent button. Use parentheses around 1 over 50. And believe it or not, this type of answer makes a lot more sense. Now, the reason it makes a lot more sense is because it actually represents the base. The base. And even though we've only been talking about this for 25, 30 minutes, a base is always greater than or less than 1. It's pretty clear that this base is greater than 1. In fact, the interesting thing is how much greater than 1. This is why I like this lesson today, because the stuff that you would do intuitively, the algebra tells you to do. That is to subtract 1. Now, if I subtract 1, I end up with the amount that's greater than 1. And we call that the rate. And I'm trying to get your brain to think like percentages today. So when you see 0.19, you do want to be able to say, okay, that represents 1.9%. You know, you move the decimal a couple places. Okay, now with this world population problem, just to kind of take you back to it, the real issue was we didn't have a percent. But now we do. Okay, but it's because we plugged into the exponential model. There's kind of like a second question in this problem, or really there is the main question, which is to predict 2030. Now, if you're going to predict 2030, you have to realize that you've already done the hard work. The hard work was to find the rate. Okay, now I can just plug in my initial value. Now, if you would like to use 6.5 as your initial value, then you're starting at the year 2000. Since you're starting at the year 2000, that would only be 30 years of growth. If you like the 1950s, which was well, I wasn't alive, but it seemed like it was a pretty fun time. If you like the 1950s, you could start at 2.5. But now you're going to need 80 years of growth. Just so you realize what I'm doing here, I'm showing you that there's 2 ways that you could finish this problem. They both end up with the same answer, at least almost the same, just because of some rounding. Okay, they end up with right around 11 billion. Right around 11 billion. Okay, now I've shown you quite a few different things today. Even though maybe none of them by themselves is the hardest thing all year, I want you to carefully think about percentages and how they relate to a base, which then can be filled in that exponential model. Okay, that's of course what the homework helper's for. Just notice the homework helper has about, 6 questions back there.